All right, so video number 3 on general on wind, and at this point we're moving toward general wind system, looking at globally that wind circulation that in fact will link to what we saw previously, because we're gonna kind of link the heating of our atmosphere with the global wind system that we observe. So remember, not so long ago we talked about the fact that our Earth was not warmed the same way by the sun, because of its orbit, but its rounded shape, and that the equator was receiving more energy per surface than the higher latitude or the poles in itself that receive less energy. So there is a distribution of energy that happens from the equator towards the poles, and that leads to a general circulation of the atmosphere, a global wind system that we can observe a long period of time, not something daily, but something seasonal, annual, that reflects, in fact, that's an equal heating of the Earth's surface with a distribution of heat and energy that depends on the season, where we can see in January, most of the warmer temperature tend to be around the equator and a little bit more toward the south. And during the summer in the northern hemisphere, we do have a warmer temperature spread much more toward the northern hemisphere. And in some way, the comparison of those two figures is kind of very big. It doesn't seem that the southern hemisphere warms up as much. And we saw that, in fact, the temperature in summer in the southern hemisphere are lower than in the northern hemisphere. And remember that the main reason is the distribution of land. There is much more land, about 2/3 of the land are inside of the northern hemisphere, 1/3 being in the southern hemisphere, which explain why the northern part, the summer in the northern hemisphere, looks warmer than in fact in the southern hemisphere. Let's see now how we can model this circulation of the wind, and in some way we try to model it so it can represent the reality, and in particular it can represent the distribution of climate that we can observe on the planet. We have a combination of several climate that is depending on the latitude, depending on the localization on the planet, and ideally based on this unequal heating of the surface of the Earth and a simple approach of a wind circulation that goes from the equator to the pole, we should be able to explain the different climate we observe. So to just make a very simple basic approach, I mean, we are considering a wind that will be blowing this warm air toward the pole. And so to simplify it, we can go more extreme, and we can consider first the planet being covered only by water. So it's avoiding the difference of heating between ground and water, and it's avoiding, of course, also to have 2/3 of the ground being on the northern hemisphere, 1/3 being in the southern hemisphere. Then we will also assume that the sun is always on the head of the equator, always the same shining. So in some way, we're not playing with the orbits and the season. We will also assume that the Earth doesn't rotate for this model, which is totally insane and not realistic, but well, it's true. It's just to simplify our system. And then with that, what will happen is, since the sunlight will mostly reach the equator right here, I mean, I should maybe make the sun this way, okay? So the sunlight is the most intense at the equator. So at the equator, we do observe convection happening, okay? The convection will happen forming clouds right here at the equator. And from that, the air will be moving directly toward the poles. And when it's reaching the poles, the air will come down because it's getting cold and it's getting dense, creating this high pressure system in the poles. And naturally, when we have to close the loop, the wind is coming back on the surface from the poles towards the equator. But it succeeded in moving the energy from the equator to the pole. If we do that, the resulting model will give us one big convection cell that I just described, which would be called a big Hadley cell. But that will make us something like that with wind at the surface that will be blowing from the northeast toward the southwest. This looks pretty okay when we look at it. Unfortunately, when we compare it to our observation, this doesn't work well. Some places, winds do not blow this. And in fact, for example, in the US, the wind tend to blow this way. So we have some kind of issues on the winds blowing in comparison to this model. Another issue will come to the fact that the Earth is rotating. And so with the rotation of the Earth, we have to introduce a force that is called Coriolis. And Coriolis will deflect, will change the wind direction from usually into the right in the northern hemisphere. And so that's something that this model doesn't take into account and in fact miss up. So let's talk quickly about Coriolis and the Coriolis force, which is in fact an apparent force caused by the rotation of the Earth. It's just a force that happens because of a different system in some way. It's just because of the rotation of the Earth that it's creating this force. And so let's look at this first little movie to give us an idea of what means Coriolis.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force, whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
Okay, so let's quickly look into this with a schematic. We are looking in this case, right here, of a go-merry round, if I'm correct with the name, sorry, that is not rotating. If you are playing with someone and you're throwing the ball to that person, the ball will just go directly at the straight line. Okay, this is easy going. As soon as you're rotating the platform, as soon as you're doing that, even though you're throwing the ball straight forward, because of the rotation, because you are part of a system that is rotating, you are the observer, you're inside of this system in rotation, you will have the illusion, the observation that the ball is in fact following a deflected trajectory, that it's not straightforward and that it is curved. This is in fact the Coriolis force, which happens to deflect everything toward the right. So the wind will be deflected toward the right in the northern hemisphere, and in the southern hemisphere, because of the same rotation, the wind will be deflected towards the left. Let's look at this video to give some more illustration and explanation about this Coriolis effect.
The Coriolis effect. As a result of the rotation of Earth, the path of any free-moving object will be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is known as the Coriolis effect or Coriolis force. We first look at the path of an airplane traveling from the North Pole toward the equator. Notice that the path of the airplane on a non-rotating Earth is a straight line from north to south. Notice that once the airplane begins to move away from the North Pole, it continues to move toward its original target at the equator. However, because Earth is rotating, the path traced out by the airplane exhibits a deflection to the right. The rotation of Earth has caused this deflection. The deflection of the Coriolis effect occurs regardless of the direction of movement. Next, we look at the path of an airplane flying west to east from San Francisco to New York City. Notice that the path of the airplane on a non-rotating Earth is a straight line from west to east. Notice that once the airplane begins to move away from San Francisco, its path is deflected to the right by the Coriolis effect. The amount of deflection from the Coriolis effect varies by latitude. The deflection is greatest at the poles and diminishes toward the equator. At the equator, there is no Coriolis effect deflection. In addition, rapidly moving objects are deflected more than slowly moving objects. The Coriolis effect influences many patterns in physical geography. For example, major ocean currents exhibit deflection to the right in the northern hemisphere and to the left in the southern hemisphere.
Okay, so in summary, if we go with the summary for the Coriolis effect, you have on this figure the non-rotating Earth, and so of course considering that a non-Coriolis force happening, and a rotating Earth and the Coriolis force happening. So the amount of Coriolis will depend on the speed of the Earth's rotation, which is something fixed, but this speed change with latitude in itself, and also it will depend on the speed of the object, the airplane or the wind in itself. All of that will play on the amount of deflection caused by the Coriolis force. However, the Coriolis will not modify the speed of the object, or it will not modify the speed of the wind. It's changing its direction. It's changing the direction in a way that something that should go straight in the northern hemisphere will be moved toward the right in the northern hemisphere. Or again, in the southern hemisphere, things have moved towards the left. And this is caused by the rotation of the Earth. The same here when we do have this plane traveling, crossing the US, they will be moved towards the north because of the Coriolis effect. And the closer to the higher latitude, the more deflection we observe because there is more and more Coriolis force closer to the higher latitude. And at the equator, there is no Coriolis force being applied, which is why, remember, we talked about hurricane not so long ago. That is why hurricanes are not starting, they cannot be born at the equator. You have to at least be at about 5 degrees latitude to observe the formation of the storm, because you need the Coriolis force to form the storm, to form the spinning that will lead to the formation of the storm. And at the equator, you don't have that spinning happening because Coriolis is not apparent. It doesn't exist. You don't have the deflection. Okay. So again, the stronger, the faster in some way the object move, the stronger the Coriolis will be, but it doesn't change the wind speed. It's only modifying its trajectory. At the end, if we do apply the Coriolis into our single model, we come with this approach, which is kind of giving us some ideas, at least, with different kind of climate going from equatorial, subtropic, mid-latitude, and subpolar regions, kind of very simple approach of the climate system, which reflects a distribution of energy that moves from the equator toward the poles. But it is kind of incomplete. And so we need to go into a more complete and more complex system, a more complex model that we will be discussing in our coming video. So see you in our fourth video.